Alright, welcome back. Let's go over quiz 2. This is quiz 2 right here. I'll write that out for you. I always forget to do the whole, put yourself in drawing mode here. Here we go. This is quiz 2. And let's go to the first question here. Which of the following is the correct Lewis structure for that formula there, right? Well, this is pretty easy. First thing we need to see here is that we have a methyl group connected to two CH2s, so that's like 3 carbons in a row with hydrogens on them, right? Well, can't be this one because that one only has 2 carbons in a row, okay? And again, can't be that one because that one only has 2 carbons in a row. So which one is it then? Well, this is not a Lewis dot structure. I don't see any electrons or anything like that. And this is a line angle drawing, so it's not that one. So the answer here is B. Again, when you're getting these questions about Lewis dot structures, go through and eliminate the ones that are impossible first, right? So that you don't waste time counting up the number of valence electrons and drawing out the central atom and filling up the octets and such. Which of the following structures have a -1 formal charge on the nitrogen, right? Well, we know that a nitrogen with 3 bonds and 2 electrons, or 3 bonds and a lone pair, is neutral, right? That's also 3 bonds and a lone pair, which is neutral. 3 bonds and a lone pair, neutral. This one is 4 bonds. So nitrogen with 4 bonds has what charge? It has a positive charge on it, right? So the only one left is this one. Number 3, 2 lone pairs and 2 bonds, that is a negative charge. So the answer there is C. Next, how many lone pairs are found on the indicated atom? This oxygen right here in the middle right there with a positive charge. An oxygen with a positive charge and 3 bonds always has how many lone pairs? 1, right? And the reason why it's like that is because normally it has 2 lone pairs, right? And it's neutral. But then when it has 3 bonds to it, one of those lone pairs is gone to form that 3rd bond, right? So that means there's only 1 lone pair left. That's what gives it the positive charge. Next, number 4. Okay, number 4. Which is the correct bond line structure for this molecular formula? Right, bond line. I like to call them line angle, whatever. Right. First thing to notice here is that we have 2 CH3s coming off of 1 carbon. Okay, 2 CH3s coming off of 1 carbon, and then the third thing that came off that that's coming off that carbon is a hydrogen, right? And the fourth thing is a CH2, right? So already we know that it's not this one right here, because that has 3 CH3s, okay? We already know it's not this one, that's only 1 CH3. We know it's not this one, that's only 1 CH3. We know it's not this one, it's 3 CH3s, right? What's the only one that has 2 CH3s connected to 1 carbon? It's this one, right? So that's structure 4. D. Next, number 5. Number 5. Okay. For the following compound, identify the lone pairs as being localized or delocalized. Okay. Well, let's take a look at the oxygen first. Okay. We know already that one of these lone pairs can participate in bonding, right? Because it is a part of the p orbital that's overlapping with the carbon below it, right? And that's why it can do resonance down here. Okay. Or vice versa. Okay. But this one here, the third one, or not the third one, but the second lone pair there, it doesn't do it, right? It doesn't do any bonding at all. Okay? So that means it's localized. So you have one lone pair that's delocalized, the one that's going to be overlapping in that p orbital with the pi bonds, with that carbon, right? And then you have one localized on that. So it's either B or C, because that one has both one localized and one delocalized in there. Okay? And then we have the lone pair that's on this nitrogen right here, right? This lone pair on this nitrogen can definitely go down, right? And make a double bond there, because that's actually, you recognize that from one of the patterns of recognition for resonance, right? An electronegative atom connected to a I'm sorry, it's a allylic lone pair, right? It's a allylic lone pair, which I believe is pattern 1. Correct me if I'm wrong down in the comments, but I'm pretty sure it's pattern 1. And since it does do this, it's making that double bond there, that pi bond, which means it's a part of that p orbital overlap, which means what? It is delocalized. So the answer is C. The answer is C. Next, identify the functional groups. We have an alcohol there, we have a ketone there, and we have a, oh sorry, that's not a ketone, I apologize. There's a nitrogen right there, so that's actually an amide. Going too fast for my own good. That's an amide. And then we have a sulfide right there. So alcohol, amide, sulfide right there, that's A. Almost done. Number 7. This is the molecule caffeine. Identify the hybridization state of each one, right? Of each of the indicated atoms, and it's pointing at nitrogens. So let's take a look at, this is actually kind of a tricky one right here. On the face of it, right, this nitrogen right here, on the amide, that nitrogen looks like it's sp3 hybridized, right? It looks like it's sp3 hybridized. But is it? There's a specific slide on one of my lectures that actually talks about the amide, right? And whether or not it's sp2 or sp3 in nitrogen, right? So let's take this entire thing and break it out and take a look at it here. A squiggly line just means there's more molecule there that I just don't want to draw. And here's another squiggly line there, right? So that's the only part we care about. That's the amide part. Okay. Remember that the amide here, or the nitrogen on the amide, has a lone pair right there. And again, looking at right there, it looks like it's sp3 hybridized because there's 4 electron domains, right? 3 bonds and a lone pair. So that's sp3 hybridized, right? But remember though that this lone pair can jump down here to form a double bond, pushing the double bond from the carbonyl up to the oxygen, right? Giving you this structure here. Another squiggly line there, another squiggly line there, and we have a negatively charged oxygen, right? That I need to fix that. That looks weird. There we go. We have a negatively charged oxygen up there, and now we have a positively charged nitrogen there, right? So now, if you look at this nitrogen, look at that. It only has 3 electron domains. Steric number 3, meaning it's actually sp2. So this guy over here is sp3 hybridized, but this resonance structure is actually sp2 hybridized, right? So which one do you choose? Turns out that the major contributor is this guy right here, the sp2 hybridized guy. Remember from my lecture, right? And the reason why is because for it to even be able to do this delocalization and form that double bond, there had to be overlapping pi orbitals, right? There had to be overlapping pi orbitals. Overlapping pi orbitals, right? And so if it's overlapping pi orbitals, it means that this lone pair is delocalized. And if that lone pair is delocalized, then it has to be sp2 hybridized, right? So that then, right, automatically crosses out, right, eliminates answers C through E, right? Because all of those say that it's sp3, and that's wrong. Okay? And so now you take a look at it, it's sp2 hybridized. What is its structure then? What is its geometry? That makes it trigonoplanar. Right? And trigonoplanar has how many, what degrees, what bond angles? 120. And so you look at your answers, A says, so atom 1, sp2 trigonal pyramidal, and B says sp2 trigonoplanar. Which one do you think it is? It's obviously B, right? Because it's trigonoplanar, like we said already. You didn't even have to figure out the hybridization of atom 2 because you figured out the hybridization of atom 1, and it's the only one that fits with the rest of them, right? So that was kind of a tricky one right there. But just remember that when you have an amide bond, right, that the nitrogen is mostly going to be in the sp2 hybridized state, right? sp2 hybridized state. Next, we have the molecule diazomethane, right? What are the formal charges of each one? Okay, well that's easy. There's a carbon there, formal charge is 0 because it has 4 bonds. There's a nitrogen here with 4 bonds, right? Which means one of its lone pair that it had is being shared with something, which means it's got a positive charge. And then we have a nitrogen here, which has 2 lone pairs and 2 bonds, which means that is a negative charge because it has an extra lone pair. So that's 0, 1, negative 1. So the answer here is 0, 1, negative 1. Answer is E. We're just rolling through these questions here, right? This is why I only give you 15 minutes on these quizzes, right? Because they're easy. So next question. Identify the resonance structure that's indicated by the arrows below. Okay. So, I mean, you can do this in your head, but for me, it's easier just to draw it out. Go ahead and draw out the resonance structure. Let's draw the skeleton first. Right? Like that. Okay. So this arrow here coming from this double bond to this bond between the carbonyl carbon and that first carbon, the alpha carbon. That means then there will be a double bond here, right? And a positive charge over here. Okay? And then, since we formed a double bond here, it breaks the double bond that was between the carbonyl oxygen and the carbon. And so that means that electron comes up here to the oxygen, right? And there's actually nothing else you have to do because the oxygen was already a carbocation, positively charged, right? And so that's all you have to do. That's the structure that should be, right? And let's see if we have that one down here. There it is right there. Structure 4, right? So for me, it's easiest just to go ahead and draw it out there. And you can see what it is. Pick from the answers after you know what the answer is. And then last but not least, number 10, for the structures shown in the box below, identify the corresponding resonance structure, right? Well, there's multiple here, okay? And the reason why it's multiple is because this carbon anions electrons can come down like that, and then this bond breaks, the one bond breaks there, and moves a carbon anion to the end. So one structure will look like this. Right? And then this same carbon anion can come down here and form a bond there. And then after it does that, this bond between the carbonyl and the carbonyl oxygen and the carbon breaks. The electrons flow back up to the oxygen, or down to the oxygen in this case. And so now you have this structure too. And you shouldn't really draw the arrow from that there because it's more like this. There we go. And those are the two structures you should have, right? So let's look for the first one first. That's number 2 right there. And then let's look for that one, and that's number 3 right there. So the answer here is D, structures 2 and 3. All right, that is all of quiz 2. Let me know if you have any questions, and I'll see you in lecture.